let's get back to this exact issue where we were here. So we want to address this question that several people asked about, which is, of course, a good thing to ask about, which is, this was cool and was even nice if we somehow magically knew there were 3 satisfying strings, we get this even faster algorithm, faster by a factor of square root 3. We would like to, work that out and take advantage of that. But also, we're going to have this issue that, how do we magically know there is 3? That was an assumption or a promise that we're not going to have in general. Well, I'm going to work on dealing with that assumption soon enough, but let's codify sort of what we know here. So in general, suppose you somehow, this is bogus for now, but somehow know there's exactly S satisfying strings. For F or C. Okay, and what I actually like to focus on is what I'll call P, which is S over 2 to the n, or S over D, which is the fraction of satisfying strings. Fraction of all strings which are satisfying. It's just a little bit nicer to focus on this fraction. It's a number between 0 and 1. Okay, and so when we were doing this analysis when S was 3, it's a little bit no longer on the board. But when S was 3, this difference vector had length 2 times square root 3 over D. The difference vector is exactly this long. And, this 3 over D, that's what we're calling P now. Okay, so in this setting, this difference vector, unif minus F, has length exactly 2 square root P. Now, assuming this length is small, that's about the same as the angle. So I'm going to continue to assume that this is small. So if P is small, and later we'll talk about maybe more details, but just imagine it's quote-unquote small, then that means the angle, theta, is very close to root P. Just the straight line distance and the circular arc distance are about the same. And so the algorithm should do about, as we saw, pi over 4 times square root 2 to the n over s repetitions of R. Okay, this was the s equals 3 case over here. And this is pi over 4 times square root 1 over p. Okay, so if p is the fraction of satisfying strings, then this is the number of repetitions of R you need to do. This is, 0.70 something. The main thing is square root 1 over p. And remember, p is a small number. It's between 0 and 1, so its reciprocal is a big number, and this gets square root of that. And our original setting, our original Grover with unique sat, p was 1 over 2 to the n. And therefore, its reciprocal is 2 to the n, and that's how we had pi over 4 times square root 2 to the n here. And what I want to emphasize here or point out is that this is kind of quadratic savings over the classical algorithm. And this quadratic savings is kind of a hallmark of quantum algorithms, or it's one thing you often can get. This square root, I'll call it square root savings. So why do I call it square root savings? Well, compare with the classical algorithm, or compare with classical algorithms. Suppose we were in this situation, but we didn't have quantum computers, we just had classical computers. So I give you this C, And somehow, magically, you know that it has exactly s satisfying strings, or like a p fraction of all possible strings satisfied. In this situation, what would you do? Like, say p is 1 in 100. Well, you just like start picking strings at random, plugging them into C, see if they satisfy. And every time you picked a random string and plugged it in, it would have a p chance of actually being a satisfying string. So how many times did you have to pick a random string and test it to find a satisfying one? Well, on average, 1 over p. So the sort of brute force randomized algorithm here, that just like pick random strings, plug them into C till you get a satisfying one. This one takes about like 1 over p, I don't know, trials. Okay, so this is the saving. So Quantum has like, this is a big number, this is the square root of that big number. So in general, Quantum gets this square root savings. Okay. So the last thing I want to talk about in this lecture for the last 8 minutes is, well, we want to remove this because this is not a reasonable assumption to assume you exactly know the number of satisfying strings. If you do exactly know what p is, and your only thing left in life is to find a satisfying string, then okay, you can exactly do this, and it'll take you about square root 1 over p time, or number of operations to find a satisfying string. But, okay, that's unrealistic. So we'll genuinely fix this in the next lecture. But let's do a few things in the direction of fixing this now. So what I want to show is that you're in good shape. In order to be in good shape, you don't have to exactly know p. If you knew p to within like 1%, that would be pretty much good enough. So this is still unrealistic, but slightly less unrealistic. Suppose somehow you knew p to within 1%. Within 1%. And what do I mean by this? So i.e., you, the algorithm, know some number, which we'll call p hat, such that p hat is between 1.01p and 0.99p. Okay, that's what I mean by like p hat is within 1% of p. Okay. So this is still unrealistic so far, but like it's a little bit less unrealistic. I'm not saying you like know p exactly. You know it's within 1%. Now, what I claim is that this is really just good enough, just as good practically. It's fine. So in this case, what you should do is just go ahead with the algorithm, pretending that p was p hat, and it'll be fine. So just define theta hat to be 2 square root p hat. And then you can check that this theta hat is within 1% of the ideal theta. The ideal theta is, the ideal theta is 2 root p. You don't know p, but you know p hat, which is pretty close to p. So theta hat is pretty close to theta. Actually, if you don't skip steps and you spend like 5 minutes checking things, you actually find it's even better. Like theta hat is probably within 0.5% of theta. But whatever, let's not try to save that. So if the algorithm now repeats our pi over 2 over theta hat times, which it can do, because it knows p hat, so it knows theta hat, so it can compute this number, and it can repeat r this many times. The final states final state vector's angle from goal is, well, let's just say the final state vector's angle is within 1% of 90 degrees in the 2D picture. Okay, so I erased the 2D picture, but before you were trying to like start at uniform and rotate basically 90 degrees. And now, not only do you have the round-off error, but like this theta is off by like, I don't know, 1%. So maybe instead of rotating by 90 degrees, you rotate by 89 degrees or 91 degrees or maybe 88 degrees. But it's similar to before. Like that's close enough. By this analysis, by this like technical analysis that we did, now it's a little bit like epsilon now is 0.01 or something rather than exponentially small. But still, if epsilon is like 0.01, then happy face is still like at least 98% or something. And that's good. So then at the end, measuring at the end gives a satisfying string maybe except with probability less than 1%. In fact, if you like really work out all the details, like it's even better. Like this is more like 0.1%. But again, whatever. And that's good because now like 99% of the time it's finding a satisfying string. And we can just declare that success. Or if we really don't like that, we can do this trick of like, okay, we'll take the final answer, plug it into C, see if it's satisfying. If it is, we'll be like, great, we found it. If it's not, we'll be like, ugh, I guess there's 1% chance hit. Well, I'll run it all over again. I'll spend twice the time. Now the probability of failing is like 1% squared. And if that's not good enough, you can run it 3 times, but it's good enough. And the last thing I want to say is, or we should double check, the total number of operations here. Well, we ran our pi over 2 theta hat times. But theta hat is basically theta. This is up to like 1%, which is 2 square root p. So this is also, again, like pi over 4 square root 1 over p, which is what we were going for. So let me just summarize in words what I've shown here. Here we saw if you magically exactly knew p, then you could find a satisfying string with about square root of 1 over p operations. Now I'm slightly improving this to say if you happen to know p to within 1%, then you can also, with about square root 1 over p, which you don't know, but you more or less know, many operations, you can also find a satisfying string. With 99% chance, but you can improve that by doing it a few times if you like. So we've kind of made like a little bit of progress on this issue of not magically knowing p. And next lecture, we'll start to build up this rotation estimation algorithm, which is kind of about finding this. Like, if you don't know anything about p, or you don't know anything about theta, how can you discover p up to 1% efficiently? So that's what we're going to try to do.